Imagine buying a house, knowing that one day, the street outside could disappear beneath 3 meters of water. For most people, that sounds like a disaster. For Dutch engineers, it's simply another design condition, because somewhere in the Netherlands, entire neighborhoods are already doing something that seems impossible. When floods arrive, the houses don't resist the water. They don't rely on massive concrete walls. They don't hope the flood never comes. Instead, they calmly rise with it. No emergency, no evacuation, no structural damage. The buildings simply float. At first glance, it looks like science fiction, but every movement is controlled by mathematics, fluid mechanics, structural engineering, and one of the most carefully designed buoyancy systems ever built for permanent housing. The remarkable part isn't that a single floating house exists. Engineers have built floating boats for thousands of years. The remarkable part is that these are complete residential neighborhoods, with roads, electricity, drinking water, fiber optic internet, sewage systems, parking spaces, schools nearby, and families living everyday lives on structures that technically never touch solid ground. For centuries, human civilization has fought water. The Dutch are beginning to ask a completely different question. What if the future isn't keeping cities away from water, but teaching cities how to float?
Every civilization leaves a mark. These are the echoes of power.
For thousands of years, cities have followed one fundamental engineering rule: find stable land, build permanent foundations. Everything else depends on that. Roads, bridges, apartment buildings, hospitals, factories. Every piece of urban infrastructure assumes one simple thing: the ground beneath it won't move. But climate change is slowly rewriting that assumption. Sea levels continue rising. Storm surges are becoming more destructive. Heavy rainfall is overwhelming drainage systems around the world. Billions of dollars are spent every year building larger flood barriers, higher seawalls, and stronger pumping stations. Those systems remain essential, but they all share one limitation: they're designed to keep water out. Dutch engineers wondered whether there was another possibility. Instead of forcing nature to obey cities, could cities adapt to nature instead? That single question completely changed how engineers began thinking about urban design. Today, the Netherlands has become one of the world's largest laboratories for floating architecture. These aren't experimental prototypes hidden inside research facilities. People actually live here. Children ride bicycles. Packages get delivered. Neighbors drink coffee on floating terraces. Meanwhile, the entire neighborhood quietly rises and falls with changing water levels. Behind this seemingly effortless movement lies decades of engineering innovation. Because building a house that floats turns out to be the easiest part, keeping an entire community functioning safely is where the real engineering begins. For more than a century, urban planners followed a predictable formula. As populations grew, cities expanded outward. New suburbs replaced farmland. Wetlands were drained. Rivers were straightened. Coastlines were reinforced. Engineers believed that with enough concrete, enough pumps, and enough flood barriers, almost any piece of land could become suitable for construction. That strategy worked remarkably well, until the climate began changing faster than infrastructure could adapt. Today, hundreds of millions of people live in low-lying coastal regions. Some of the world's most important cities, including New York, Miami, Jakarta, Bangkok, Shanghai, and Amsterdam, face increasing flood risks from rising sea levels, stronger storms, and heavier rainfall. Traditionally, the engineering response has always been defensive. Build a higher seawall, raise the riverbanks, install larger pumps, construct stronger flood barriers. Each solution works, but only up to a point. Every additional meter of protection becomes dramatically more expensive than the one before it. Larger walls require deeper foundations. Bigger pumps consume more energy. Higher dikes create greater consequences if they ever fail. Dutch engineers recognized something important. Floods themselves were becoming increasingly difficult to predict. Instead of designing cities around yesterday's water levels, Future cities would need to survive tomorrow's uncertainties. That realization changed everything. Rather than asking, "How do we stop the water?" engineers began asking, "What if water is no longer the problem?" That simple shift transformed the entire design philosophy. Instead of treating floods as rare disasters, they started treating rising water as another engineering load, just like wind, earthquakes, or snow. If buildings could safely carry thousands of tons of weight, could they also safely float? The answer wasn't borrowed from architecture. It came from naval engineering. Ships had already proven that enormous steel structures could remain stable for decades while floating. Offshore oil platforms had demonstrated how floating systems could survive violent storms in open oceans. The challenge was no longer whether floating structures were possible. The challenge was adapting those engineering principles to something people could call home. And solving that problem required engineers to answer one deceptively simple question. How do you build a concrete house that floats? At first, the idea sounds impossible. Concrete is one of the heaviest building materials on Earth. It's used to sink bridge foundations, anchor offshore platforms, and support skyscrapers weighing hundreds of thousands of tons. So how can an entire concrete house possibly float? The answer begins with one of the oldest principles in engineering. Not architecture, not construction, physics. More than 2,000 years ago, Archimedes discovered that any object placed in water experiences an upward force equal to the weight of the water it displaces. Today, every cargo ship, every aircraft carrier, every offshore platform, and every floating neighborhood still follows exactly the same principle. The material itself doesn't determine whether something floats. Its overall density does. Imagine placing a solid block of concrete into a lake. It sinks immediately. Now imagine taking that same amount of concrete and shaping it into a giant hollow box. Suddenly, everything changes. Inside that hollow structure is a large volume of trapped air. The total weight increases only slightly, but the amount of water displaced increases dramatically. Eventually, the upward buoyant force becomes greater than the downward weight. The structure floats. That's exactly how Dutch floating homes are engineered. Beneath every house sits a massive reinforced concrete caisson. Think of it as the hull of a ship, hidden below the living room instead of below a deck. The walls are heavily reinforced. The internal chambers remain watertight, and every dimension is calculated long before construction begins. Engineers first estimate the permanent structural weight: concrete, steel, walls, roof, windows. Then they add every possible live load: furniture, residents, appliances, snow accumulation, maintenance equipment, even future renovations. Then comes something even more important: safety factors. No professional engineer designs a floating foundation to float perfectly at its maximum load. Instead, additional buoyancy is built into the system. If the calculated total load equals 100 tons, the foundation is designed to safely support considerably more. That reserve buoyancy ensures stability during unexpected loading conditions. But floating isn't the real challenge. A raft also floats. The real challenge is remaining perfectly stable while people walk inside, while strong winds push against the walls, and while waves continuously try to rock the entire structure. That's where the engineering becomes far more sophisticated. Because a floating home isn't designed like a boat. It's designed to behave as if it were built on land. If you've ever stood on a small boat, you know exactly what engineers wanted to avoid. Every step changes the balance. The floor rocks beneath your feet. Even gentle waves create constant motion. Now imagine that happening inside your living room every day. Very few people would want to live there. So Dutch engineers approached the problem differently. Instead of designing floating houses like boats, they designed them like extremely stable floating platforms. The first step is increasing the width of the foundation. A wider floating base creates a much larger footprint in the water. That immediately improves stability. Next comes weight distribution. Heavy mechanical equipment, water tanks, utility systems, and structural elements are positioned as low as possible. This lowers the center of gravity. At the same time, the center of buoyancy remains higher within the floating foundation. The relationship between these 2 points determines whether a structure naturally returns to level after being disturbed. Push the house slightly to one side. The buoyant forces automatically generate a restoring moment. Instead of continuing to tilt, the structure gently returns to its original position. The movement is so small that most residents barely notice it. But stability alone isn't enough. A floating house could still drift away during storms. That's why every home is connected to massive steel guide piles driven deep into the ground beneath the water. These piles don't carry the weight of the house. The water does that. Instead, they function like elevator rails. The home can move only in one direction, straight up or straight down. It cannot slide sideways. It cannot rotate. It cannot drift across the lake. Even during severe storms, the guide piles keep the structure precisely where engineers intended. The result is something remarkable. A home that can rise several meters with floodwater, yet feels almost indistinguishable from a traditional house built on solid ground. But solving the foundation created another engineering puzzle. If the entire house moves up and down every day, how do electricity, drinking water, internet, and sewage pipes move with it, without ever breaking? Asterisk asterisk. Keeping a house afloat is impressive. Keeping an entire neighborhood alive, that's a completely different engineering challenge. Think about your own home. Every essential service enters through fixed underground infrastructure. Fresh drinking water, electricity, natural gas, fiber optic internet, sewage. Those systems work because the building never moves. Now imagine lifting that same house 3 meters into the air. Rigid pipes would snap. Electrical cables would tear apart. Sewer connections would fail almost instantly. So Dutch engineers borrowed another idea from offshore engineering. Instead of rigid connections, they designed infrastructure that could move. Every floating home is connected to shore using flexible utility corridors. Fresh water travels through reinforced flexible pipes capable of bending thousands of times without fatigue. Power cables are installed with carefully calculated service loops. Extra cable length hidden beneath floating docks. As the house rises, the loop slowly unfolds. When the water recedes, gravity allows the cable to return to its original position. The same principle applies to fiber optic internet. Unlike traditional copper wiring, fiber cables are extremely sensitive to excessive bending. Engineers therefore specify minimum bend radii, protective conduits, and controlled movement zones so communication remains uninterrupted even during major floods. Sewage presents perhaps the greatest challenge. Gravity normally carries wastewater downhill, but a floating house constantly changes elevation. To solve this, Dutch engineers use sealed pressure systems combined with lift pumps inside the floating foundation. Wastewater is collected, temporarily stored, and pumped through flexible pressure pipes toward the municipal sewer network. The homeowner never notices. Flush the toilet, take a shower, wash the dishes. Everything functions exactly like a conventional home. The engineering remains invisible. Even emergency services are considered. Fire hydrants, electrical isolation systems, communication lines, and maintenance access points are all designed with movement in mind. Nothing is left to chance, because if even one utility fails, an entire floating neighborhood becomes unlivable. Yet despite all these moving systems, residents often forget they're living on water at all. And that's exactly what good engineering is supposed to do. When it works perfectly, you don't notice it. Designing one floating home is difficult. Designing hundreds requires engineers to think like city planners, naval architects, structural engineers, and environmental scientists, all at the same time. Construction doesn't begin on the water. It begins in a controlled factory environment. The reinforced concrete floating foundation is cast inside a dry dock, where engineers can precisely control dimensions, reinforcement placement, and waterproofing quality. After curing, the dock is gradually flooded. For the first time, the foundation begins to float. This is one of the project's most important engineering tests. Sensors verify buoyancy. Engineers measure trim, the difference between the front and rear waterline. They check for unexpected rotation, structural deflection, and watertight integrity. Only after passing every inspection does vertical construction begin. The house itself is then built directly on the floating platform, much like a conventional building. Walls, insulation, plumbing, electrical systems, windows, and roofing are installed while the structure remains afloat in a protected construction basin. When complete, powerful tugboats carefully tow the finished home through Dutch canals toward its permanent location. It's a remarkable sight, not transporting building materials, but transporting an entire completed house across the water. Once it arrives, cranes aren't needed. The floating foundation naturally positions itself between previously installed steel guide piles. Engineers secure the guidance system, connect utilities, test every service, and integrate the home into the neighborhood's digital monitoring network. But a floating community isn't simply a collection of houses. It also needs floating streets, pedestrian walkways, parking solutions, stormwater management, public spaces, and safe evacuation routes. Every element must rise and fall together as one coordinated system. In many ways, engineers aren't just constructing buildings anymore. They're building an entirely new category of city, one that treats water, not as an obstacle, but as its foundation. For decades, climate adaptation meant building bigger seawalls, bigger pumps, bigger flood barriers. But Dutch engineers have started asking a different question. Instead of making flood defenses taller every decade, could cities themselves become flood defenses? It's a subtle difference, yet it changes everything. A traditional neighborhood is designed around one fixed elevation. Every road, every foundation, every utility line depends on the assumption that the ground stays dry. When that assumption fails, everything fails together. Roads become rivers. Electrical substations flood. Homes suffer structural damage. Recovery can take months, sometimes years. Floating neighborhoods work differently. The flood isn't an unexpected disaster. It's already part of the engineering calculations. Whether the water rises 50 centimeters or 3 meters, the building behaves exactly as it was designed to. Its foundation continues floating. The guide piles continue stabilizing. The utility connections continue flexing. To the homeowner, the flood becomes almost invisible. This is known as resilience engineering. Instead of preventing every possible failure, engineers design systems that continue functioning during failure. The distinction is incredibly important because climate scientists predict that future weather will become less predictable. Engineers can no longer design only for historical averages. They must design for uncertainty. That's why Dutch floating communities are filled with sensors, water level sensors, wind monitors, foundation movement sensors, electrical monitoring systems, structural health sensors. Together, they create a digital twin of the neighborhood. Every movement, every load, every environmental condition can be monitored in real time. If something behaves unexpectedly, engineers know immediately. This isn't simply housing anymore. It's intelligent infrastructure, a living engineering system that continuously monitors itself. And that's precisely why governments around the world are beginning to pay attention. Because the Netherlands may not be solving a Dutch problem. It may be solving a global one. The world's population continues growing. At the same time, coastal land is becoming increasingly valuable. Ironically, it's also becoming increasingly vulnerable. That creates one of the biggest engineering challenges of the 21st century. Where will future cities expand? For centuries, the answer was simple: build farther inland. Today, many countries no longer have that luxury. Land is limited. Housing demand continues rising. Climate risks continue increasing. Floating urban development offers an entirely different possibility. Instead of reclaiming land from water, cities can expand directly onto it. Lakes, reservoirs, protected bays, harbors, even former industrial waterfronts, all become potential building sites. And unlike traditional construction, floating neighborhoods leave the water ecosystem largely intact beneath them. Sunlight still reaches the water. Natural water flow continues. Marine habitats experience far less disruption than large-scale land reclamation projects. The technology is already evolving beyond individual homes. Engineers are now developing floating apartment buildings, floating parks, floating farms, floating solar power systems, and even concepts for entire floating districts connected by bridges and autonomous water transport. Some designs combine renewable energy, rainwater harvesting, heat pump systems, battery storage, and smart grid technology. The goal isn't simply to survive floods. It's to create self-sufficient communities that produce much of their own energy while adapting naturally to changing water levels. Of course, floating cities won't replace every traditional city. Mountain towns don't need them. Desert communities don't need them. But for millions of people living along vulnerable coastlines, they may become one of the safest forms of urban development ever created. The Netherlands has spent centuries fighting water. Today, its engineers are demonstrating something even more remarkable. The future may not belong to the cities that resist nature, but to the cities engineered to live with it. For centuries, human civilization believed that strong cities had to stand on solid ground. Dutch engineers challenged that belief. They proved that stability doesn't come from refusing to move. It comes from moving intelligently. Floating neighborhoods represent more than an architectural innovation. They represent a completely new philosophy of engineering. Don't fight every natural force. Understand it, design around it, and use it to your advantage. As climate change reshapes coastlines across the world, the lessons being learned in the Netherlands could influence how millions of people live in the decades ahead. The future of cities may not be higher. It may be lighter. It may be smarter. And it may float. This is Echoes of Power. If you enjoyed this documentary, subscribe for more stories exploring the world's greatest engineering achievements, mega projects, and innovations shaping our future. Thanks for watching. We'll see you in the next one.